In this video, I want to review the quiz that we would have taken on Friday had we seen each other, and then also I want to talk a little bit about simplifying radicals or square roots. This will give us a bit of a preview for what we're going to see in the next few days. So as far as the quiz goes, I'm going to walk through most of the odd question problems on the left-hand side, and I would ask that you complete the even-numbered problems as well. There are only 10 questions total, so if I walk through, maybe I'll do all 5 of the ones on the left. If I walk through all 5 of those, that'll leave 5 for you to complete on the right. So let's get to it. This worksheet should be available in Schoology. However, if you can't find it, feel free to copy from this video. Now, our instructions are real clear in indicating that we are solving each of these equations by factoring, and that should trigger a thought in your mind that when we factor, we should have an equation equal to 0. And once we have that, then we'll set each factor equal to 0 and solve from there. Hopefully those will be a little bit easier and more manageable. Now, I will note that in this first example, while it looks like a non-standard trinomial at first, there is a GCF. And we always check for a GCF first. After I factor the GCF out of this, I'm left with 2 times the quantity of n squared minus n minus 2 equals 0. And then inside, I'm now left with a standard trinomial. And that's what I would be looking for if there was no GCF to begin with. Now that I've gotten the GCF out of the way, I run through the list again. Standard trinomials are much easier to solve than non-standard, so this is good for us. I'm looking for, since it is a standard trinomial, 2 numbers that multiply to make 2, that add or subtract to equal 1, and more importantly, they have to multiply to equal -2 and add or subtract to equal -1. So it looks to me like the number -2 and +1 would be good for our factors. Now keep in mind that these are factors and not solutions yet, and to obtain the solutions, we set each of these factors equal to 0. And then solve. Now, if you've seen enough of these to where you can identify the solution pretty easily without writing out the equation, I'm okay with that at this point. We have seen a bunch of them, but I do recommend writing out the equation if you're at all hesitant so that you can verify that you're obtaining the correct answer. Now, if there was no GCF and this wasn't a standard trinomial, then we would learn to look for, or we should know to look for non-standard trinomials. And with non-standard trinomials, most of us in class have been using the guess and check method to factor them. And then finally, if the problem that we're encountering doesn't fall into any of these categories, if they don't have the characteristics of these 3 types of factoring situations, then we would hope and look for a factor by grouping context. If the equation doesn't fall into any of these 4 categories, well then we're just going to have to take a timeout from it, because at this point in Algebra 2 we haven't learned any other factoring methods to help us just yet. Moving on to number 3 here, again I notice that there's a leading coefficient, but this time there's no common factor throughout, so this is going to be a non-standard trinomial that needs to be factored. It's already set equal to 0. So what I'm hoping to find are 2 factors that multiply to make a, the 2 value up front, 2 factors that multiply to make c, the value at the end, so that when we FOIL them back together, we end up with a +1 in the middle. So my first guess might be 3 and 2 here, and when I double check this, the outside products make 4n, the inside products make 3n. And that's a good sign because a +4 minus 3 would get us back to this +n. So in order to land on a +4n, I'm going to put my plus sign here. And in order to land on a -3n, I'll put my negative sign here. Now we can't stop yet. These are just factors. They're not solutions. So we have to set each factor equal to 0. So 2n minus 3 set equal to 0. N plus 2 set equal to 0. So if I add 3 to both sides, I'm left with 2n equals 3. And then if I divide both sides by 2, I see that n is equal to 3/2. And I prefer that answer as opposed to the decimals or a mixed number fraction. Leave it as an improper fraction, please. And then over here, similarly, we can follow the process and see that n in this case is equal to -2. In a problem like 5, before we can even try to solve this, we do have to make sure that the equation is set equal to 0. So I'm going to subtract v and subtract 21 from both sides. That way I've got all of my terms on the left-hand side, and more importantly, this first term remains positive. That makes it a little bit easier to solve. We're again dealing with a non-standard trinomial. There are no GCFs here, and there is a leading coefficient other than 1. So I'm going to guess 2v times v will multiply to make 2v squared. And now I'm thinking about the numbers that multiply to make 21. We've got 1 and 21 and 7 and 3. So again, I want to use 7 and 3 because those two are closer to one another, but I don't have any real good clues here. So I'm just going to say 7 and 3 and see how lucky we get. Well, as it turns out, the 2v times 3 does equal 6v. And 7 times v equals 7v, and that's a good sign for us, because if we're trying to FOIL back together to make -v, then I would say a -7v plus 6v would make that happen. So in order to end on the plus 6v, I'm going to put my plus sign here, and in order to end on the -7v, I'll put my minus sign here, and I think we've got a good factor. Again, if you've had enough practice, you'll know that by adding 7, or by setting this a factor equal to 0, we could add 7 to both sides and then divide by 2, and that's going to leave us with 7 over 2. And with the factor on the right, we see that our solution would end up being -3. So again, I hope that helps with solving equations by factoring. I've got 3 other examples of those here within the worksheet that I expect you to be able to do on your own. Now moving on to the examples down below, if we were to use the same techniques that we've been practicing all along, well, this number 7 gets kind of interesting, or not interesting, I guess, depending on how you look at it. Normally we'd have the equation set equal to 0, so I'm going to subtract 6 from both sides in the hopes of moving this 6 to the left, and we'd have an equation equal to 0 from there. But as it turns out, it ends up canceling on both of these, and we have x squared equal to 0. And now we can ask ourselves what numbers multiply together to equal 0, and as it turns out, x itself has to be 0, and only 0. Well, let's try this guy down here, number 9. If we were to divide both sides by 10, that would leave us with b squared equals 34. And I chose to do this here because I think most of you would try this technique. And a lot of you would recognize at this point, well, b is not quite by itself. We would have to take the square root of both sides. As we had mentioned in class, if we have to put the square root symbol on paper, if it wasn't there to begin with, then we have to be prepared for 2 solutions, a positive and negative result. Now, I don't want to go reaching for a calculator every time, so it's going to be our job this week to recall or learn how to simplify this expression, and if we can simplify this expression. In this case, I don't think that there is a nice way to simplify it, so we would leave our answer like this. For those of you that are paying close attention or wondering, since this is a quadratic equation, it has a power of 2, we should see 2 solutions, but I've only got 1 box. Let's remember that this plus minus sign indicates that there's a positive result and a negative result. Positive square root 34 and negative square root 34. I'm going to jump back to number 8 here and revisit this notion of solving by factoring. Kind of got sidetracked with those 2 examples here, but this is kind of neat. If we had used the same technique that we have been used to so far, by moving all components to one side of the equation and setting it equal to 0, in this case we'd end up with -3n squared plus 147 equals 0. We might notice that there is a GCF here of -3. So I'm going to factor that negative 3 out. And I'm going to be left with n squared minus 49 equals 0. And since this is a trinomial of sorts with the term missing in the middle, we can pretend that there's a plus 0n minus 49 if it helps us see this a little bit better. We might recognize that the factor for this expression would be n plus 7 and n minus 7, because 7 times negative 7 equals negative 49, and 7 plus negative 7, or 7 take away 7, is also equal to 0. So our factors are were easy enough to find. They're nice solutions here, or nice factors, I should say, that lead us to solutions. The value for n has to be either negative 7 or positive 7. Now, if we had used the plain old square root method that we were just talking about a minute ago, we could divide both sides by negative 3. So let me just show this problem one more time. If we had divided both sides by negative 3, like we did in the problem number 9, we'd end up with n squared equals 49. Actually, that was in, number 9. We'd have n squared equals 49. Now we put the square root down on paper because it wasn't there to begin with, and we have to be aware of the two solutions that are presented. And the square root of 49, in this case, since we're looking for both solutions, would also be positive and negative 7. We got the answer, the same answer, in two different ways. The method in blue is sort of the newer technique. The method in red was the old tried and true factoring method. Now, when it comes to radicals, simplifying them is going to be an important component in this class, because some of our solutions that we calculate to problems, we would like to have the exact answers to. And when you take a square root and punch it into a calculator, the calculator is going to return a result that contains a decimal, most likely, and decimals inherently just aren't as accurate. So I'd like to point something out about radicals here for just a moment. We know that if we take the square root of the number 4 times 9, that's essentially the same as taking the square root of 36, and that's because 4 times 9 equals 36. And vice versa. If I saw the square root of 36, I could split that apart as the square root of 4 times 9. Now, interestingly enough, the square root of 36 is 6. Notice I'm only calling it positive 6 here because the square root symbol was already on paper for us. Take a note also that the square root of 4 times the square root of 9, separated from one another, not together underneath the square root symbol, but separated, would be the square root of 4 is 2, and the square root of 9 is 3, would be 2 times 3, and that also equals 6. So that's helpful for us. If we recognize that the square root of 4 times 9, where 4 times 9 both sit underneath the square root, and the square root of 4 times the square root of 9, where we have two separate radicals, when we notice that both of these are actually equal to one another, that's a very helpful property for us as we move forward in this class. And we can, moved my screen here. And we can say that in general, for any pair of numbers, the square root of a times b underneath the radical would be exactly the same as the square root of a times the square root of b. If we find it useful and helpful, we can actually separate a radical into two smaller pieces. So let me show you how and why that might be important for us. We may be asked to find the square root of 450, or to simplify the square root of 450. And that's a rather large number, so it's a bit hard to interpret right now. But you may recognize that the number 9 times 50 is 450. So we could take the square root of 9 times the square root of 50, and that would be equal to the square root of 450. Now, this is particularly helpful because do you recognize what the square root of 9 is? Well, that's just the number 3. 3 times the square root of 50 is another way to represent the square root of 450. Similarly, you might recognize that the square root of 25 times the square root of 18 would equal the square root of 450, and that's because 25 times 18 is 450. So we could make the claim here, since the square root of 25 is 5, that 5 times the square root of 18 is also equivalent to 450. Now lastly, the number 225 times 2 is equal to 450. So therefore the square root of 225 times the square root of 2 is equal to the square root of 450. And you may or may not be aware, but the square root of 225 is 15, and now we have 15 times the square root of 2 as yet another way to report or simplify the square root of 450. And so we can note that the square root of 450, 3 times the square root of 50, 5 times the square root of 18, and 15 times the square root of 2, they all mean the same thing. They are all 3 different ways to write the same number. But as it turns out, we like 15 times the square root 2 the best. At least in our world of Algebra 2 and higher level mathematics, we like this one the best. And we say that it's the simplest form because the radicand, or the number underneath the radical symbol, has no more factors that are perfect squares. Or in other words, there's no number inside of this radical symbol that can be divided by a number that has a square root. For example, 18 could be divided by 9, and 9 has a square root. 50 could be divided by 25, and 25 has a square root, so that makes these not an ideal answer. 2, on the other hand, has no other factors at all, much less a factor that's also a square. So we like 15 times the square root 2 the best. And if you follow these 2 statements here, you can see how we could take the 3 times square root 50 and 5 times square root of 18 and simplify them both down into the same most simplified result. We wouldn't be satisfied at the square root of 50, so we can split it apart into 2 products, square root of 25 and square root of 2. Square root of 2 has no other factors inside of it, but we do recognize the square root of 25 is 5. So with 5 and 3 acting as essentially like terms, we would multiply those 2 together to obtain 15. We're left with a square root of 2. Similarly over here, the 18 was factored into 9 and 2, and it follows the same procedure here. The square root of 2 is retained, and the square root of 9 is 3. While we combine these like terms by multiplication on the outside of the radical symbol, 5 times 3 is again 15, with a square root of 2 left behind. So we'll talk about the rules in general at another point in class, but just to finish out this particular video, let's take a couple of these samples and try to simplify them the best we can. I think 3, 4, and 5 would be pretty good for now. Now the way I would simplify the square root of 12, this is number 3, taking the square root of 12. The way I would do this is I would use a factor tree. We've already talked about prime factorization in this class, how we can break a number down into all of its prime components. So we're going to do the same thing again here. And if you recall, we could use a tree method, or we can also use mental arithmetic to do this as well. But I'm going to note that 12 is the same as 4 times 3. So therefore, the square root of 12 is the same as the square root of 4 times the square root of 3. Now the number 3 is a prime number. It can't be factored any further, so I'm going to leave that one alone as it is. But as far as the square root of 4 goes, we notice that the square root of 4 is 2, and that's because 2 times 2 equals 4. At the end of this factor tree, and if I eliminate the radical symbols, it's easier to see. At the end of this factor tree, at the end of these branches, we always end up with prime numbers. Now, anytime that there are two prime numbers attached to the same value here, we recognize that these two prime numbers that are identical are indeed the square root of the branch that it came from. So by considering this factor tree, we might think of the square root of 12 as the square root of 4 times the square root of 3, where the square root of 4 is actually equal to the number 2, and the square root of 3 has no additional factors. So we could stop there and report this as a simplified result. It may not look any more simple than what we started with, but in mathematics we call this the simplified result because we've now reduced the radical essentially to its smallest value. With problem 4, we were asked to simplify the square root of 50, and sometimes with larger numbers the factor tree method is a bit harder to follow, at least to produce a nice expression like this. So we'll just keep breaking this thing down. I'm looking at each of these tree branches, and I'm trying to decide if at the end of each branch if we see a prime number or not. Now again, 2 times 25 is what made 50. 5 times 5 is what made 25. At the end of these branches, we continue to divide into two numbers that multiply to make the level above it. Well, this square root of 50 wasn't too bad after all, was it? It was a bit larger, but it actually factored in much the same way that we saw a moment ago. We see a pair of these 5s that are sitting underneath the 25, so we can state that the square root of 50 is simply the square root of 25 times the square root of 2, and we know the square root of 25 is 5, and 5 times the square root of 2 would be a nice simplified answer for the square root of 50. So let's try this last one. Now with the square root of 32, you could probably use a factor tree a variety of different ways here. In fact, for a lot of these problems, you can use a factor tree in different ways. Some of you might see that the square root of 32 would be equal to the square root of 2 times the square root of 16. Some of you would see the square root of 4 times the square root of 8, and that would be just fine as well. Back here, some of you may have even been thinking, well, the square root of 50 is really just the same as the square root of 5 times the square root of 10. And if you thought any of those were appropriate factoring methods along the way, you'd be 100% correct. Let me just reiterate that it doesn't matter which factor method that you end up using. As long as you fully factor and create a complete factor tree, you will obtain the same answers when we're all done. Let's go with this thought, 2 and 16. Now 2 is a prime number and 16 can be divided into 4 and 4. And just like before, we see that the square root of 32 could be reported as the square root of 16 times the square root of 2, because we have this common factor branch that stemmed from the number 16. And the square root of 16 is 4, and we'll leave the square root of 2 behind because it has no common factors. But what if we had factored this into 4 and 8? Well, 4 can be split into 2 and 2. 8 can be split into 4 and 2. And this 4, again, can be split into 2 and 2 once more. Well, now you might notice that the square root of 32 should be written as the square root of 4, because of this factor branch, times the square root of 4, because of this factor branch, times the square root of 2, because this guy is the last fruit that's laying by itself. We recognize the square root of 4 is 2. Another square root of 4 is 2. And the square root of 2 leaves or stays behind untouched. But lastly, we can combine these like terms, multiplying on the outside of the radical symbol, to make 4 square root 2. And those two solutions are the same. So there are lots of different ways that we can simplify radical expressions, especially those that contain variables and different indices or a different index to their root. We'll spend some time talking about that this week when I see you in class again. Please make sure that you refer to the instructions that I've got posted in Schoology and submit a picture of your work before the end of the day today so that you can receive a homework credit for this particular assignment while I'm out of the building. Thanks for watching.